Hi, I'm Raina Fitzgerald, and in this lesson we're going to look at graphing linear inequalities. Here in our first example, we have the inequality y is greater than or equal to 1/2 x plus 1. Well, we start by looking at the 1/2. The 1/2 represents the slope. This is in the form y equals mx plus b. The 1 represents our y-intercept. Let's go find those on the graph. The y-intercept is y equals 1. The slope is 1/2. Up 1, our rise, over 2. 1, 2. So let's put our next point in. And here we have 2 points. Now these 2 points form a line. And if we look back at the original equation here, we do have that y is actually equal to 1/2 plus x. It's greater than or equal to, but it's also equal to. So this is our boundary line right here. So to draw that line, we connect these points. So let's go ahead and draw that line. So this is a region that's bounded by the line y is equal to 1/2 x plus 3. Now we have to determine where to shade, because when we're talking about an inequality, we actually are going to have a shaded region of points. And what we want to do is, the best way to do this is to test the origin. The origin is 0, 0. By testing the origin, if we find that this equation works for the origin, then we know our shaded region is this region underneath our boundary line. If in fact we discover that the origin is not valid for this inequality, then we want to shade the region that's above the boundary line. Let's go ahead and test the origin with the original inequality. The original inequality says, and we'll write this in red, that y is equal to and also greater than. So will y be greater than or equal to 1/2 x plus 1 when x and y are equal to 0, 0? Well, to replace y with a 0 here, is this greater than or equal to 1/2 times an x value of 0 plus 1? Well, the left-hand side is 0 of this inequality, and the right-hand side is 1/2 times 0 is 0 plus 1. So the right-hand side is 1. Well, 0 is not greater than or equal to 1, so this is a false statement. And since this statement is false, we know that this point right here, the origin, is not valid for this inequality. Well, we know that this line is valid, and every value then beneath the line is not valid, but all values above the line will work. So what we want to do, and I'm going to shade this with lines, is we shade above our boundary line. So these lines represent our shading, and this is our answer. So when you think about this answer, I want you to think about the entire Cartesian coordinate system here. If this line were to continue this way forever and up this way forever, this entire region under the line, all of the ordered pairs, and there are many, many points, all of these points, or I should say none of these points, satisfy this inequality. However, all points that sit on this line, or all points that are above this line, and there are an infinite number of them, will satisfy this inequality. When we're solving for an inequality, the solution itself is the shaded region. And this is our solution. Here we have another inequality. Y is greater than 2/3 x plus a negative 1. Notice that this one is greater than. There is no equal sign. So when we decide what this boundary line looks like, we're going to have to dash the boundary line to indicate that no point on this line will actually satisfy this inequality. It's only satisfied when y is greater than this line. So if we're looking at this, what we see is to create our boundary line, we see that it's of the form y equals mx plus b, so the slope is 2/3, and the y-intercept, b, is negative 1. The boundary line itself is y is equal to 2/3 x plus a negative 1/2. So our y-intercept is at negative 1 right here, and our slope is 2/3, which means we're going to go up 1, 2, that's our rise, and our run is 1, 2, 3. So now we've found another point which is on our boundary line right here. Now we want to connect these points into a line, which is our boundary line. But our boundary line, because in fact when we look at the original equation, y is not equal to this line, our boundary line must be dashed. So here's my boundary line. I'm going to go through these points, but I'm making a dashed line, and this is freehand, so it's supposed to be straight, but it's not perfectly straight. So this line says that I have created two regions, and this is the boundary line that separates the region. The line is dashed because there's no equal sign here, and so any point sitting on this line will not satisfy this inequality. Now what we want to do is test the origin. The origin is always the easiest value to test because it's simply 0, 0. If the origin works, then we know that the region above the boundary line satisfies this inequality. If the origin does not satisfy this inequality, then the region below the boundary line satisfies the inequality. So let's take our original inequality, which is y is greater than 2/3 x plus a negative 1. And we'll go ahead and put in the points x 0 and y is 0 for our origin. So here y is 0. Is this greater than 2/3 times 0 plus a negative 1? Well, the left-hand side is 0, and the right-hand side, well, we can see that 2/3 times 0 is 0. This is gone. So it's 0 plus a negative 1. Excuse me, the left-hand side is 0, the right-hand side is negative 1. And in fact, it is true that 0 is greater than negative 1. So this statement is true. Since this statement is true, we know the region that should be shaded is the region that holds the origin. So our shading, and I'll go back to blue, again, in this particular case, the shading is above our boundary line. One way that this is different than the last example is that in the last example, our boundary line was solid. But in this example, because y is greater than but not equal to, in the original equation, our boundary line is dashed. So the solution to this inequality is this picture we see right here, this graph, indicating that this region holds all the points that satisfy this inequality, not including the boundary line. Here we have another example. Y is less than or equal to a negative 1/2 x plus 3. This equation, again, is in y equals mx plus b form. So the boundary line is y is equal to a negative 1/2 x plus 3. Here, our slope is 1/2, negative 1/2, and our y-intercept is 3. Let's go find those. Our y-intercept is at 3, 1, 2, 3. So I'll put a 3 here, and let's put a point right where our y-intercept is. Now our slope is negative 1/2, which means we're going to go down 1, our rise is negative, our run is positive, 1, 2. So our next point for this line falls here. Now we can connect these 2 points to find our boundary line. And in this case, because y is less than or equal to, our points will actually exist on the boundary line. So our boundary line will be solid. So let me draw this. Again, this is freehand, so I try to keep it as straight as I can. So here's our boundary line. It's solid, which means all points that exist on this boundary line satisfy this inequality. But now the question is, do we shade and select all points above this line or below this line? There are 2 regions, above and below. What we do here then is we check our origin. The origin is 0, 0. It's in the lower region. If this point 0, 0 works for our original inequality, then we know we shade in the region that's below. If the origin does not work for this inequality, then we shade the region above. So let's go ahead with our inequality, which is y is less than or equal to negative 1/2 x plus 3, and we're going to plug in a 0 for x and a 0 for y, which means 0 is less than or equal to a negative 1/2 times x, which is 0, plus 3. Well, the left-hand side is 0, and the right-hand side is 3. This is a true statement. 0 is less than 3, which means the origin satisfies this inequality. So our shaded region will be below the line. All points that fall on this line and below this line satisfy this inequality. So our answer to this inequality is this graph displaying the shaded region. Here's another example of an inequality. In this inequality, y is less than, but not equal to. So when we create our boundary line, we know our boundary line must actually be dashed. And our boundary line is y is equal to 1/3 x plus 2. This is in slope-intercept form, where 1/3 is our slope, and 2 is b, our y-intercept. So let's put our y-intercept in at 2. And our slope is 3, which means from 2, we're going to go up 1 over 1, 2, 3. So here's our second point right here. Now remember, y is not equal to this line. So when we draw this line, it's a boundary. So we have to make a dash line. We have to draw a dash line that's going to go between these 2 points, or connect these 2 points. So here's our boundary line. Now we have to check the origin. Does the origin satisfy this inequality? The origin is 0, 0. Going back to the inequality, which is y is less than 1/3 x plus 2, we're going to plug in the values for the origin. Here, y is 0, and x is also 0. The left-hand side is 0. Is 0 less than 2? This is a true statement. Since this is true, the origin is a valid point that satisfies this inequality. So we want to shade underneath our boundary line. So there are an infinite number of points that will satisfy this inequality, and they all fall under the boundary line. They do not include the boundary line. This graph represents our solution to this inequality.